Good morning, good afternoon, and good evening. Welcome to the Crazy Hat Chemist. So here we go again with another grand video on the behavior of gases. This is a pencil and paper, or actually a pen and paper example of what we've got going on here, which is the behavior of gases worksheet number 3. Let's see if we can hammer this out, and we will have a fantastic day. All right, so let's see here. So a few assumptions before we get going. Number one, I'm assuming that you know your nomenclature. If you don't, you should go watch my YouTube videos on nomenclature. In addition to that, you should also know chemical reactions. If you don't, you should watch my YouTube videos on that as well, and you should know your stoichiometry. If you don't know your stoichiometry, well, by goodness, watch that too. I'm also assuming that you have a periodic table. I am using this one right here. It's from the SAT subject test, and hopefully one of these days they'll bring that back again. And then I'm also assuming that you know a number of other things here. And so that is the following information right here. So I'll point this out here for you. Okay, so these are the mathematical equations necessary to do the equations or to do the mathematical problems within this unit here of gases. So this first one right over here is called the general or combined gas law. This is P1V1 over T1 equals P2V2 over T2. Okay. This one right here is the general or combined gas law with the pressure being held constant. That is Charles' law. You should probably know the graph for that. It's V1 T1 equals to V2 over T2. That's Charles' law, where the pressure is held constant. Gay-Lussac's law is where the volume is held constant, and that's P1 T1 equals P2 T2. And then the last possibility of the combination or general gas law is Boyle's law, where the temperature is being held constant, P1 V1 equals P2 V2. Then we have Dalton's law of partial pressures. That is, the total pressure is equal to the sum of all the individual pressures. This is typically used in a problem where it says over water, or when you collect a gas over water. That's commonly used here. Then we have Avogadro's law, and that's V1 over N1 is equal to V2 over N2. Then we also have the ideal gas law. PV equals nRT. That's the ideal gas law. R is the gas constant. And then we have Graham's law, where the rate of one gas compared to the rate of another gas is equal to the square root of an inverse relationship of either their molar masses or their densities. Okay, this is where the gases are at the same temperature. That's critical in order to use this equation. A derivation of the ideal gas law of PV equals nRT is the density of gases. Density is equal to PM over RT. R is the gas constant, just like it is in the ideal gas equation. P is for pressure, T is for temperature, and M is for molar mass. D is for, of course, density. And then we have STP conditions. This is 273.15 Kelvin and 100 kilopascals. Your textbook might have a 1 atmosphere, and that would be fine too, but I'm using the 100 kilopascals, which is actually the correct value. At STP, you should know that 1 mole of any gas is equal to 22.414 liters, and that is coming from the stoichiometry unit. You might want to review that. And then you should know some pressure conversions. Check with your instructor if there are other pressure conversions that he or she would like you to know. But so the pressure conversions that I'm using are 1 atmosphere equals 760 millimeters of mercury equals 760 torr equals 101.325 kilopascals equals 1.013 bar. Okay, and Torricelli was the Italian scientist that designed and came up with the mercury barometer, and that's why it's torr for Torricelli. And then millimeters of mercury, well, he actually used mercury for his barometer. All right, so let's get moving on this worksheet here. we've got our calculator handy, of course. We've got our worksheet handy, and we're going to be doing the behavior of gases worksheet number 3. And let's see if we can work out these problems here. All right, let's get moving. All right, so it says a gas occupies 32 milliliters. This tells me milliliters tells me that this is a volume. And then it says at 128.7 kilopascals. The kilopascals tells me it's a pressure. And it says, what is the pressure? So I'm going to call this volume 1. This is pressure 1. What is the pressure? That's going to be pressure 2. That's my unknown. That's what I'm solving for. If the conditions are changed to 0.0184 liters. And liters tells me it's a volume, and that would be volume 2. All right, this is a direct example of Boyle's law where the temperature is held constant. It doesn't mention anything about temperature, though therefore temperature is remaining constant. So Boyle's law is PV over T equals PV over T. Actually, this is the combined gas law. But with Boyle's law, the temperature is being held constant. So I'm just going to scratch that out there. And now I actually have Boyle's law, where the temperature remains constant. And it's an inverse relationship with regards to pressure and volume. Whereas Charles and Gay-Lussac's law is a direct relationship. Okay, this is an inverse relationship. That means if the pressure goes up, the volume goes down. All right, so what we need to do is we need to make sure that our volumes are in the same set of units, and one of them is in milliliters, one of them is in liters, so we need to make sure that they're both in the same set of units. What we're going to do this time here is we're going to convert the 0.0184 liters, and we're going to convert that into milliliters. So here we go. A little bit of unit canceling right here. Not too bad. This is a really easy, simple one. Okay. And you should know this unit conversion, that is 1 liter is equal to 1,000 milliliters. These are an infinite number of significant figures because this is a definition for both the 1 liter and the 1,000 milliliters. Remember that leading zeros are not significant figures. Do they count? Yes, they do count because they're important for placeholdership, but they are not significant figures. So I'm going to say 0.0184 times 1,000 divided by 1. And then I'm going to get my answer here, and that will be 18.4 milliliters. That's my new volume here. And that's maintaining the same number of significant figures that we had previously, and that is 3. That has 3 significant figures. All right, so that is this number at volume 2. So let's start plugging into this equation here of Boyle's law, and let's see what we can hammer out here. All right, so P1 is going to be 128.7 kilopascals. And then we have a volume of 32 milliliters, And that's going to equal our new pressure. That's what we're solving for. That's pressure 2. And then our new volume that we have converted into the milliliters, and that's 18.4 milliliters. Okay, hopefully that looks really fancy and nice there. I like that. What we're going to do, this is a multiplication division here. And we're looking at significant figures. This has 4 significant figures right here in this number. This has 2 significant figures in this number, and this has 3 significant figures in this number right here. So the fewest number of significant figures is 2. Okay, so what we're going to do is divide both sides by 18.4 milliliters. 18.4 milliliters. And you should see that the milliliters cancels out. All right. Hopefully that makes sense. So into our calculator, we're going to type the following information: 128.7 times 32 divided by 18.4. And I'm going to solve for my new pressure, which will have the fewest number of significant figures of these numbers, and that is actually 2. So I'm going to get 220 kilopascals. And that number has 2 significant figures. That's a 1, 2 significant figures. And this is a trailing 0, but there's no decimal in the number. So that 0 actually does not count as a significant figure, but it is important for placeholdership. Okay, so hopefully you understood that one. All right, so here we go. Let's keep on going and see what we can do here with the next problem. This is going to be problem number 2. So we're going to slide this on up. Remember, again, this is the behavior of gases worksheet number 3. If you haven't watched my other 2 videos on the worksheets, I have the behavior of gases worksheet 1 and 2. Those are 2 separate videos. This is the 3rd one here. So please check those out. And of course, you should be watching the YouTube series on the behavior of gases collection of the lecture series before you actually even attempt to do these problems. All right, so let's move this on up here or down, however you view that as, and here we go. All right, so this next problem here, number 2, what do we have here? It says a gas at 16.5 milliliters. That is most certainly a volume because milliliters. And then we have 1.6 bar. That is most certainly a pressure. And 56.7 degrees Celsius. That's a temperature. So I got V1, P1, and T1. And then it says what temperature? So that's temperature 2. That's my unknown. If the conditions are changed to kilopascals, that's going to be a pressure. 105.3 kilopascals, and then 0.052 liters. That's my second volume. All right, so you should see that my volumes right here are not in the same set of units. So at some point in time, I either have to convert the milliliters into liters or the liters into milliliters. Doesn't really matter. In addition to that, my pressures, if I look at my 2 pressures, one of them is in bar, one of them is in kilopascals. It would make sense if you convert either the bar into kilopascals or the kilopascals into bar. One or the other, it doesn't matter. You could convert the bar into millimeters of mercury and the kilopascals into millimeters of mercury. That just seems a little bit more work. You do have to convert this temperature into Kelvin. So that's a must also, because all gas laws must have the temperatures in Kelvin. All right, let's see if we can knock this one out of the park too, just like what we did with the last one. I'm going to convert these 16.5 milliliters into liters. So 16.5 milliliters, and we're going to convert this into liters. So this is opposite what we did on the previous problem. That's why I'm solving converting this one here. All right, so what we have is 1,000 milliliters equal to 1 liter. This is an infinite number of significant figures because that's a defined unit conversion. This has 3 significant figures. I'm going to maintain the number of significant figures. So I'm going to have a 0.0165 liters. So I've maintained the number of significant figures that were in the original number, which is 3, and that's 1, 2, 3. These leading zeros are important for placeholders, but they are not significant figures. All right. Now, let's see here. Now, what we're going to do is we're going to do the temperature conversion here. Might as well do the temperature conversion. We have 56.7 degrees Celsius. We're going to add 273.15. And we are going to round with the fewest number of decimal places, which is 1. So my answer is going to have 1 decimal place. Okay. And that will be 329.9 Kelvin. That is, again, rounded to 1 decimal place. So I've got my temperature converted, got my volume converted, and now I need to do my pressure. So again, arbitrarily, I'm just going to pick one of these pressures. I'm going to take the kilopascals at 105.3 kilopascals, and I am going to now convert that into bar. That's probably one of the simplest ones I can do. So let's sketch that out here. So we know that 101.325 kilopascals, that's equal to 1.013 bar. And you should see that the kilopascals cancels out. This has 4 significant figures, and these are both infinite because they're defined. So I'm going to maintain the number of significant figures, which is 4. So this will be 1.053 bar. Okay, fantastic. So now I have done all my volume, my temperature, and my pressure conversions respectively. And so what we need to do is plug this into the appropriate gas law, which is the combined or general gas law. So I'm going to write that down here. That's P1 V1 over T1 is equal to P2 V2 over T2. Right. So if you followed my lecture, what I did on my lecture is I rearranged these problems and solved for them and then plugged in afterwards. So that's why I'm not doing that here, because you can watch that on my lecture series. But what I'm going to do is just plug directly in here. All right, so I have, what do I have? My first pressure is 1.6 bar. And my first volume is in liters now. That's 0.0165 liters. And then my temperature, I converted my temperature from degrees Celsius to Kelvin. So that's 329.9, 329.9. That's Kelvin. And then I have my second pressure. Go. My second pressure is where'd it go? Here we go. 1.053 bar. And my second volume is right here, 0.052 liters. And I am solving for temperature number 2. Okay, so we're going to look at significant figures. This is multiplication division. This has 2 significant figures. This has 4 significant figures. This has 3 significant figures. Remember, leading zeros don't count. This has 4 significant figures, and this has 2 significant figures. Leading zeros don't count. I'm solving for T2. Okay, so what you're going to do is plug this into your calculator. You're going to plug in the following. 329.9 times 1.053 times 0.052 divided by 1.6 divided by 0.0165. I'm going to get T2. I'm going to round that to 2 significant figures, and that will be 680, and the units are Kelvin. There's no decimal on this number. That tells us that these 2 numbers here are the significant figures that we're looking at here at this moment in time. All right, that is problem number 2. And so hopefully that worked out well for you. Just a quick little advertisement note here. You are watching The Crazy Hat Chemist, and please subscribe to my YouTube channel. I would greatly appreciate that. And watch my YouTube series, lecture series. And heck, if you really want to, watch my cooking videos as well. There's some pretty cool cooking videos to watch. All right, so our next problem here, without further ado, is right here, number 3. Okay. All right, let's see if we can hammer out number 3. Let's see, a gas occupies a volume of, and it says volume, but those liters tells me it's a volume. 2.36 degrees Celsius, that's temperature, and 257 torr, that's a pressure. These are all the same set of conditions. It says calculate the volume. We're going to call that volume 2 if the conditions are changed to STP. So STP. So the standard, the S is for standard, the T is for temperature, P is for pressure. So standard temperature and pressure. At the beginning of this lecture, I delineated out what the standard temperature is. Standard temperature is 273.15 Kelvin, and the standard pressure is 100 kilopascals. Both of these have an infinite number of significant figures here. Okay, and these units on both of these will dictate what we use for the other portions of this. So 100 kilopascals, we're going to convert this torr into kilopascals. And as always, we always convert the temperature into Kelvin, but that one's at Kelvin. So we're going to solve for the second volume. This is hopefully obviously a combined or general gas law. But what we're first going to do is we're going to first do our temperature conversion here. So that's 2.36 degrees Celsius plus 273.15. And that's going to equal, we're going to add these two numbers and we're going to have two decimal places. So that's going to be 275.51 Kelvin. Okay, so that's our temperature 1 now. And then the other thing that we're going to do is we're going to convert these torr into kilopascals. That way we maintain the infinite number of significant figures on this 100 kilopascals, which is a defined value anyways. So we're going to say 257 torr, and we're going to convert this into kilopascals. So here we go. Let's see if we can nail this down here really quick. All right. That's 760 torr, and then 101.325 kilopascals. Okay, and you should see that your torr values, they cancel out. This has three significant figures. This is infinite, and this is infinite because these are definitions here at this moment in time. And so we're going to take 257 times 101.325 divided by 760, and we're going to round that to three significant figures, which would be 34.3 kilopascals. Okay, all right, fantastic. Now what we're going to do is we're going to write down what the combined gas law equation is, combined or general gas law. So P1V1 over T1 equals P2V2 over T2. Okay. So the last problem, what I did is I solved for T2, and this time we're solving for V2. So I'm trying to give you as many examples as is possible here. So we're going to plug these values in here. So we're going to start off with our P1. Our pressure one is the 34.3 kilopascals. And our volume one is 0.487 liters. And our temperature one, let's see if we can write that down here. Our temperature one is 275.51. 275.51 Kelvin is equal to so we are solving, oh yes, we have pressure of 100 kilopascals. Volume 2 is what we're solving for, and our temperature is 273.15 Kelvin, just like that. So because this is at STP conditions, the standard temperature, infinite number of significant figures, standard pressure, infinite number of significant figures. I have 3, 4, 5 significant figures here in this temperature. Leading zeros don't count, so this has 3 significant figures, and this has 3 significant figures. So I'm going to have 3 significant figures after I'm done with this problem. So just like what we did before, we're going to do crisscross applesauce as far as the multiplication and solving for V2. So in solving for V2, what are you going to plug into your calculator? 34.3 times 0.487 times 273.15 divided by 275.51 divided by 100. I'm going to get V2, and that is going to be equal to 0.166 liters. And that's rounded to 3 significant figures. Leading zeros don't count, remember. Another question that was popped up here, and I'll just do that here for this one here off to the side here just a little bit, but the other way to do this is to rearrange this equation and solve for what I'm looking for. So I'm going to rearrange this and solve for V2. So I'm going to show you how you do that. Essentially, you're going to do the same thing as if you have the numbers plugged in there. You're cross multiplying. Okay, so P1, V1, P1, whoops. P1 V1 is equal T2 is equal to T1 P2 V2. and I'm solving for V2. So what we're going to have to do is divide both sides by T1, P2, T1, P2, and then I'm just going to rearrange this. So I have V2 is equal to, and these cancel out here, P1, V1, T2, T divided by T1, P2. So this is effectively what you're plugging into that. And you could look at the V1, T1, P1 and plug those in as appropriate. And you're solving for V2. That's what we're doing here. And then you know that this is the T2 and the P2 right there. And you could plug those in and you're going to get the same thing that we just got right over here. So hopefully that's going to work out for you and be effective as well. Let me do one other thing. On the previous problem, we had the same general or combined gas law, which is P1 V1 over T1 is equal to P2 V2 over T2. And so what I'm going to do is I'm going to solve this for T2. So I'm going to rearrange and solve for T2. So just as far as the equation goes, let's see if we can hammer that out. Again, we're cross multiplying. So T1 P2 V2. T1 P2 V2 is equal to P1 V1 T2. P1 V1 T2. Okay, and we are trying to solve for T2 right there. So we're going to divide both sides by P1 V1, P1 V1, and these cancel out, and you're left with T2 is equal to T1 P2 V2 over P1 V1 right there, just like that. Okay, and this can work with, what is it, problem number 2. So if you could plug right into this, this is using it with problem number 2. I'm just going to give you a numeric example of why this works here like this. And this is probably the more complicated one in solving for one of the temperatures as opposed to problem number 3, you're solving for the volume. Most students tend to get that, but let's just do a simple math example. And if we have, let's say, 3 over 5 is equal to 2 over x. Okay, so there are a couple of easy ways to solve for this. One of them is cross multiplying, like what we're doing here, and I won't multiply out the 5 and the 2. I'll just keep that separate, as 5 times 2 is equal to 3 times x. And then what we do is we divide both sides by 3, and then we get x is equal to 5 times 2 over 3. And then that's 10/3, right? An alternate way of doing this, and maybe this works out well for you, is we want to isolate this x. So we're going to multiply both sides by 1/2. That gets rid of that there. Now, there still is a 1 in the numerator here. So right now I have, right now I have 3 over 2 times 5 is equal to 1 over x. And then what we're going to have to do is take the reciprocal of this side and the reciprocal of that side. And then you get x is equal to 2 times 5 over 3. And you should see that both of these two things are equal, right? 5 times 2, that's 10. 2 times 5, that's 10. Divided by 3, divided by 3. They're both equal. So they're the same thing. We're effectively doing that same kind of math, but with letters instead of numbers. Hopefully the numbers are really, really easy. The letters may be a little bit more difficult, but hopefully not too much of a stretch. All right, so that was number 3. Again, you're watching The Crazy Hat Chemist, and please subscribe to my YouTube channel and all that kind of good stuff. So I'd greatly appreciate it. Pass it on my YouTube channel to your aunts, your uncles, your cousins, maybe some people in a different country, and maybe I can get some good subscribers coming from other countries. That would be fantastic. All right. Let's see here. So this next problem, number 4, let's see if we can hammer this one out. Says we have 34.8 milliliters of a gas is collected over water. Over water. So by the way, this is a volume. Since it's collected over water, we're going to be using Dalton's law. right here is a temperature and the atmospheric pressure. This is the measured pressure. This is the total pressure right here, the total pressure. The atmospheric pressure is 779.2 millimeters of mercury. And then it says the vapor pressure of water is this. Notice that the two temperatures coincide. This vapor pressure of water is actually a tabled value that's coming from a book. It's generally the Handbook of Chemistry and Physics. Okay. That would be your reference. And then what is the volume of the dry gas at STP conditions? And again, we just worked with STP conditions. That is 273.15 Kelvin at the temperature, and the pressure is equal to 100 kilopascals. Again, both defined values with an infinite number of significant figures. All right, so well, golly, what do we need to do here? What we need to do here is that this pressure is in torr and this pressure is in millimeters of mercury. So I need to convert this torr into millimeters of mercury. That's probably the easiest thing to do here. So I'm going to have 18.436 torr, and I'm going to convert this into millimeters of mercury. Now, some of you can actually do this right in your head. You're saying, yo, crazy hat chemist, why are you actually writing this out? Well, I want to make sure that everybody understands how to do this problem. Okay, but torr, and I'm going to have millimeters of mercury up here, right? So it's 760 torr is equal to 760 millimeters of mercury. That is 1 torr equals 1 millimeter of mercury. So the torr is going to cancel, and I'm going to be left with 18.436 millimeters of mercury. So that's the same set of units that my total pressure is in. Okay, fantastic. All right, so now what we're going to do is use Dalton's law. And Dalton's law is the total pressure is equal to the partial pressure of water in this case, plus the pressure of the other gas. It doesn't say what the other gas is, so pressure of gas, we'll just say that. Okay, so what we do have is we have the total pressure, that's 779.2 millimeters of mercury. And we just converted the partial pressure of water from torr to millimeters of mercury so that our units can cancel out and we can actually do this subtraction. So that's 18.436 millimeters of mercury plus the partial pressure of gas, right? So simple math problem right here. We're going to subtract this 18.436 from both sides. And the partial pressure of the gas is now going to equal 760.8 millimeters of mercury. Okay, so that's the partial pressure of the gas when the gas was collected over water. All right. Now, the next thing that we're going to do is we are going to now convert this this millimeters of mercury, we're going to convert this into kilopascals because our pressure, that standard pressure, is in kilopascals. So we're going to do a unit conversion with this one here. Let's see if we can squeak that out really quick. This is the correct number. It's just the incorrect set of units here. So we're going to have 760 millimeters of mercury and 101.325 kilopascals. And so the millimeters of mercury are going to cancel out. And then we're going to do 760.8 divided by 760 times 101.325. And we're going to get 101.4, 1 decimal place, kilopascals. All right. Now I have the pressure of just the gas in the correct set of units. Whew. All right, fantastic. One other thing that we need to do is we need to convert the temperature into Kelvin. So that's 20.8 degrees Celsius plus 273.15. That's going to equal, I'm going to round it to 1 decimal place here. So that's 294.0 Kelvin. So that's my other temperature. So now what I have are the following. I have 34.8 milliliters. That's my volume. I have my pressure at 101.4 kilopascals. I have my temperature at 294.0 Kelvin. Then that's the wet gas that's collected over water. Then I am going to solve for the volume of the dry gas at the following pressure, standard temperature and pressure, which is right here. So that's condition 2. All right. So I'm going to move this down here, and then I'm going to write the combined gas law. So that's P1 V1 over T1 is equal to P2 V2 over T2. All right. Hopefully that's looking good for you. So what we're going to do is we're going to plug directly into this here in just a moment. All right, so here we go. We're going to keep on going with this wonderful problem that we see before us here. And so P1, what is P1? That is this value right over here. So this is 101.4 kilopascals. And then V1, that's 34.8 milliliters. And here we go. And our temperature, temperature 1 is 294.0 Kelvin. So I've got that. And then we have standard temperature and pressure. So the standard temperature, 273.15 Kelvin. And the standard pressure is 100 kilopascals. And I'm solving for V2. Okay. So just like what I did before and showed you before what to do, we're going to cross multiply and solve for V2. We're going to be looking at significant figures. This is 4 significant figures. This is 3 significant figures. This is 4 significant figures. Trailing zeros count with a decimal. This is an infinite number of significant figures and an infinite number of significant figures. So the fewest number of significant figures I have in this problem is 3. So what we're going to do is we're going to slide this on up here just a little bit. We're going to solve for V2, and plugging into our calculator, we're going to do the following. 101.4 times 34.8 times 273.15 divided by 100 divided by 294.0. I'm going to round that to 3 significant figures, and that will be 32.8 milliliters. Okay, fantastic. That is my correct numeric value. What I'm going to do is zoom on out on this problem just a little bit so you can see the whole entire problem here that we have before us. There we go. There's the whole entire problem. All right, so a Dalton's law problem because it's gas collected over water, an excellent problem. It's at STP conditions, standard temperature and pressure. When it says STP, that tells us what those temperature and pressure values are. And then I'm going to convert all the temperatures and pressures into these values. Okay. All right, so there's just a overall recap of that entire problem over there. So hopefully everybody's okay with that. Just looking at that here, making sure everybody's good. Hopefully I went through that stepwise okay for you. All right, so let's check out the next problem, and that would be problem number 5. All right, so problem number 5 says which gas is slower and by how much in comparing oxygen with dinitrogen heptoxide. Okay, so oxygen is diatomic. That's O2. And dinitrogen, so it's nitrogen oxide. Dinitrogen is right there. That's 2. Hept is for 7, and that's right there, just like that. Okay. So it says which gas is slower and by how much? So we got 2 questions to answer. Number 1 is which gas is slower. We'll answer that here in just a minute, and then we're going to answer the how much problem here in just a moment. So we first need to get the molar masses of both of these. So oxygen is O2. We're going to look at oxygen on our periodic table, and we're going to take 16 times 2. It has 2 decimal places. So the molar mass for oxygen is 32.00 grams per mole. And the molar mass for dinitrogen heptoxide, we're going to take nitrogen, 14.007 times 2, plus 16.00 times 7, and then sum those up and round it to the fewest number of decimal places, which is 2, and that will be 140.01 grams per mole. Those are the respective masses for oxygen and dinitrogen heptoxide. So, so imagine this is by the way, this is an example of Graham's law. Graham's law is comparing gases at the same temperature and the rate of diffusion or effusion. And so diffusion is like someone sprays perfume or opens up an orange or a banana in a room, and eventually everybody will smell it. The gases diffuse throughout the room. Okay, it's kind of like if you imagine a pebble being thrown in a crystal lake, and then you see those concentric rings. So the gas is being diffused out like those rings on a lake. Effusion is gas moving out of a small opening in a container. So like if there's a hole in your wall, then gases will effuse out of that hole in the wall, just like in a balloon. So here's how it works. Since they're at the same temperature, these two gases, that's oxygen and dinitrogen heptoxide, since they're at the same temperature, they have the same kinetic energy. And if they have the same kinetic energy, then their speed is based on their mass. So imagine if I'm on a skateboard and you push me. And then I get in my pickup truck, full-size pickup truck, four-wheel drive, and then you push me in that. It's in neutral, okay? So the skateboard weighs less, has less mass, has less density, and therefore it will move faster with the same amount of kinetic energy in comparison to the pickup truck that you're going to push, right? So that's what we're comparing. So therefore, since oxygen has a lower molar mass, it's faster. And dinitrogen heptoxide has a higher molar mass, it's slower. Okay, so now we've answered our question, which one is slower? Yeah, it is the dinitrogen heptoxide is the slower because the mass is larger. Now we're going to answer the question of how much slower the dinitrogen heptoxide is. So this is Graham's law. The rate of dinitrogen heptoxide compared to the rate of oxygen is equal to an inverse of their square roots of their molar masses or their densities. So notice that this is oxygen and this is the oxygen's molar mass. It's a reciprocal, an inverse of their molar masses. And then this is for dinitrogen heptoxide. That's going to be down here at 140.01 grams per mole. Okay, one of the things here, by the way, this has 4 significant figures. This has 5. You're going to have 4 significant figures in your answer. Okay, and so you're going to take 32 divided by 140.0, take the square root of that, and then you should get the following number in your calculator to 4 significant figures, 0.4781. Okay. And then that number is in your calculator. So really this is a ratio. Notice that the grams per mole cancels out. This is a unitless number. This is just the rate of dinitrogen heptoxide is traveling at a rate of 0.4781 in comparison to the rate of oxygen, which is traveling at a rate of 1. Right? What's the denominator of 2? 1. What's the denominator of 1,000? 1. Okay, so if the number that you get when you do this, if the number is less than 1, then that gas is slower by that amount. Okay. As a converse to this, I'm just going to throw this in here. Rate of oxygen over the rate of dinitrogen heptoxide is equal to 1 over the rate of dinitrogen heptoxide and oxygen. So it's the reciprocal. So if I were to do 1 over 0.4781, that would equal 2.092. Again, I'm running with the correct number of 4 significant figures. The denominator of this number is also 1, like any number. So that means that oxygen is traveling at a rate of 2.092 times faster than dinitrogen heptoxide, which is traveling at a rate of 1. Again, the faster gas has a number greater than 1. The slower gas has a number less than 1. Remember, dinitrogen heptoxide is traveling at a rate of 0.4781, and oxygen is traveling at a rate of 1. You can still see that oxygen is traveling faster, a rate of 1, than dinitrogen heptoxide. Okay, hopefully that settles up Graham's law for you and answers both questions, which one is faster and by how much, and which one is slower and by how much. So I've got both of them on there for you. All right. Let's hammer out problem number 6. So here is problem number 6. It says, what is the density of trinitrogen pentoxide at 745.4 millimeters of mercury and 36.33 degrees Celsius? So trinitrogen pentoxide. So nitrogen oxide, tri, that's 3. Pent is for 5. We're looking for the density. So density is equal to, and what is my name? My name is Phil. That's my first name. What's my last name? Montbriand. And then what am I? I am a teacher. And where do I teach? I teach at Rio. So Phil Montbriand is a Rio teacher. So this is the density equation. So I'm going to actually be plugging into this right here. Okay, here we go. All right, so the first thing that we do when we use the density equation is we use the gas constant R. That's 0.0821 liters, atmospheres, and moles Kelvin. Probably the biggest mistake that students do is that they don't plug in the gas constant first, and they are lazy and they don't plug in the units. The units tell you what the units need to be for the other components, that is the pressure, the molar mass, and the temperature. Since we are dealing with a gas problem, then obviously, hopefully, the temperature needs to be in Kelvin. So I'm going to convert my Kelvin, I'm going to convert my degree Celsius temperature into Kelvin, and that is going to have 2 decimal places. So that's going to be 309.48 Kelvin. So I'm going to plug that in here, 309.48 Kelvin. All right, and then, so this is effectively a defined value. That's an infinite number of significant figures. This has 5 significant figures right here. All right, then the other thing that we need to know is we need to know the pressure, and that pressure needs to be in atmospheres because that's what the units of pressure are for the gas constant. So I'm going to do this off to the side down below here. I'm going to take the 745.4 millimeters of mercury, and we are going to convert this into units of pressure of atmospheres. So a real simple conversion here for you. Again, 760 millimeters mercury and 1 atm. Again, this is an infinite number of significant figures for my unit conversions. This is 4 significant figures. So I'm going to maintain 4 significant figures, and this number is going to be 0.9808 ATM. And we're going to plug that in right over here. So that's 0.9808 ATM. Again, this enables me to cancel out the atmospheres. This enables me to cancel out the Kelvin. And you should see that I have liters, moles there in the denominator still. The M is going to be for the molar mass. So we're going to look at our formula, trinitrogen pentoxide. So we're going to pull out our periodic table. And 3 times 14.007 plus 5 times 16.00. I'm going to round it to the fewest number of decimal places, which is 2. And so that number is going to be 122.02 grams per mole of trinitrogen pentoxide. Okay, and then you should see right here that the moles cancels out. What I'm left with is in the numerator grams, in the denominator liters. Okay, this number has 4 significant figures. This number has 5 significant figures. So my ending significant figures are going to be 4 significant figures. I'm going to plug this into my calculator. I'm going to take a 0.9808 times 122.02 divided by 0.0821 divided by 309.48. I'm going to round that to 4 significant figures, and that number is going to be 4.710 grams per liter of N3O5. Okay, fantastic. That's my answer. That's what we got. And hopefully that worked out well for you too. That's looking like a fantastic answer. I'm really pretty happy about that. Remember, you're watching the Crazy Hat Chemist, and the Crazy Hat Chemist is cruising through more problems here on gases. So let's do number 7. Where is number 7? There's number 7. Here we go. All right. So number 7, it says, what is the volume in milliliters? So we're looking for volume in milliliters. We have 0.390 grams of fluorine. Does everybody remember the formula for fluorine? Well, fluorine is one of the diatomic elements that is going to be F2, diatomic. The following conditions apply. This is kilopascals, that's a pressure, and 23.6, that's a temperature in degrees Celsius. Do you have 2 of anything? The answer is no. Okay, so since you do not have 2 of anything, we are going to be using the ideal gas law. So that is PV equals nRT. And we are solving for the volume. So what we're going to do is we're going to rearrange this and solve for volume. We're going to divide both sides by pressure. And then we're going to get volume is equal to nRT over P. So what we're going to do is we're going to set this up so that we're ready to rock and roll with this. The first thing that we're going to do, like on every one of these ideal gas problems, or anything that requires density of gases, or anything that requires the gas constant, is we're going to first plug in the gas constant, 0.0821 liters atmospheres over moles Kelvin. Remember, again, you need to make sure that you have the number and the 4 units that are associated with the gas constant. Okay. So this needs to be moles of fluorine, because that's N. This needs to be temperature in Kelvin, and this needs to be pressure in atmospheres. So that the gas constant atmospheres tells me that my pressure needs to be in atmospheres. The Kelvin tells me that the Kelvin temperature, as in all gas problems, needs to be in Kelvin. And the moles, the amount of gas, needs to be canceled out. And I'm going to be solving for liters. I know that this question is asking for milliliters, but we're going to convert from the liters into the milliliters at the very end. Okay, so what we're going to do is we are going to first convert this and get our moles. So we're going to have 0.390 grams of F2. And we're going to convert this into moles. Hopefully you remember this from the stoichiometry unit. The stoichiometry unit never goes away, but this is an easy conversion. So that's grams of F2, 1 mole of F2, and we're going to get a numeric value here. We're going to look on our periodic table, and we're going to say 19.00 times 2, and that will be 38.00, 38.00. And then we're going to take 0.390 times 1 divided by 38.00. And we're going to round that to 3 significant figures. Trailing zeros count with a decimal. That 0 doesn't count. So we'll have 1.03 times 10 to the negative 2 moles of F2. I'm going to plug that where it belongs. That's 1.03 times 10 to the negative 2. And that's the moles of the fluorine. All right, now what we're going to do is we are going to do the next one, and that's do our temperature conversion. I'll do that right down below here. A different color here. So 23.6 plus 273.15. I'm going to round it to 1 decimal. And so this is going to be 296.8 Kelvin. And I'm going to place that right here, 296.8. And I already have my units of Kelvin. I have one more unit conversion to do, and that's going to be atmospheres. I'm going to take this pressure at 109 kilopascals. And I'm going to convert that into atmospheres. Now, I hope everybody understands the reason why I'm going to these specific units again. I'm going to these specific units of moles, Kelvin, and atmospheres. Because the units in the gas constant have those set of units. So 109 kilopascals, I'm going to cross out the kilopascals. I'm going to have an infinite number of significant figures here, infinite number of significant figures here, and I got 3 significant figures. I'm going to maintain that 3 significant figures. So it's 109 times 1 divided by 101.325, and I'm going to get 108 ATM. Notice the number doesn't change a whole lot, but it does change a little bit, 108 ATM. All right, so now I'm ready to solve for my volume. It will be in liters. My answer needs to be in milliliters, so we're going to do one quick little thing at the end. So in our calculator, we're looking at significant figures. This is 3 significant figures. This is infinite significant figures. This is 4 significant figures, and this is 3 significant figures. So I'm going to plug into my calculator 1.03 times 10 to the negative 2 times 0.0821 times 296.8 divided by 108. When I do that in my calculator, I'm going to round it to 3 significant figures. I'm going to get 0.232 liters. And then what we're going to do is we are going to convert this into milliliters, because my question was asking for milliliters. So we need to do that here. That won't take too long. 1 liter, 1,000 milliliters. This is an infinite number of significant figures, infinite, and this has the 3 significant figures. So 0.232 times 1,000 divided by 1, I'm going to get 232 milliliters of fluorine. That's F2. So I got number, units, and formula, and I've got my correct number, units, and formula rounded with 3 significant figures. Fantastic. Whew. All right. Hopefully you're still hanging on here with me. We got 2 more problems to do, and then we're going to be done with this 3rd worksheet. And this is just like awesome, cool stuff. And then you're going to be ready for this unit test. All right. So we're going to move this on up here, and we're going to go to our next problem. That is number 8. Okay. All right. So here we go. Number 8. It says, what is the mass, grams? That's going to be our units here. It's going to be grams. I have a volume. That's because it's milliliters. I have carbon tetrachloride. That's CCl4. I have millimeters of mercury, that's a pressure, and I have degrees Celsius, that's a temperature. So do I have two volumes, two pressures, or two temperatures? The answer is no. Since I do not have two of any of those, what I need to do is I need to use the ideal gas law. And the ideal gas law is PV equals nRT. By the way, this is the ideal stepwise solutions of gas problems, of course, right? All right. So we have, what do we have? We have the gas constant always. We have the volume. We have the pressure. We have the temperature. What we don't have is the number of moles. But we are asked to solve for a mass in grams, but you can convert from moles into mass, hopefully very simply with one step. So what we're going to do is solve for the N, which is the number of moles, rearranging the ideal gas equation, dividing both sides by RT. So I'm going to have N is equal to PV over RT. Okay. So I'm going to set this up here, just like I set up the last problem. The first thing that you do is you plug in the gas constant 0.0821. And that's right, folks. Don't forget the units. That's liters, atmospheres, over moles, Kelvin. Okay. And so right here needs to be my temperature in Kelvin. This right here needs to be the pressure in atmospheres. And this right here needs to be the volume in liters. And then how did I know that so quickly, what everything needs to be? Well, the gas constant tells me what the units are for all the other components. So the temperature must be in Kelvin. That will enable me to cancel that out. The volume needs to be in liters, and that will enable me to cancel that out. The pressure needs to be in atmospheres, and that will enable me to cancel that out. And what will I have in the denominator? Well, 1 over moles, and then I'm going to take the reciprocal of that because that's in the denominator, and I'm going to get moles. All right, so what do I need to do is I need to first convert all these pressure, volume, and temperature into the correct set of units of atmospheres, liters, and Kelvin, respectively. Plug into this equation, solve for the number of moles, and then convert that into grams using the molar mass of carbon tetrachloride. All right, so let's start off with this pressure. We have 392 millimeters of mercury. So going to convert this into atmospheres. 760 millimeters of mercury and 1 atm. And these are an infinite number of significant figures, 3 significant figures. So I'm going to maintain that. Millimeters of mercury cancels out. 392 times 1 divided by 760. That's going to equal 0.516 atm. And I'm going to place that right where it belongs at 0.516 atm. All right, fantastic. Then I'm going to solve for my volume term. That's 172 milliliters. I'm going to convert that into liters because that's what the ideal gas equation specifies for units. That's 1,000 milliliters, 1 liter. Milliliters cancels out. Infinite number of significant figures, 3 significant figures, and I'm going to have a 0.172 liters. That's going to go right here. 0.172 liters. I already got my units in there. No way. And then I have one more conversion to do, and that is my temperature conversion. So I'm going to take the 107.0 plus 273.15 Kelvin. I'm going to round this to 1 decimal place. And so that is going to be what? 380.2 Kelvin. So 380.2 Kelvin. Fantastic, just like that. I'm going to cancel out those units. And we're going to get what we want. So in our calculator, we're going to say 0.516 times 0.172 divided by 0.0821 divided by 380.2. I'm going to round to the fewest number of significant figures. This is 3 significant figures. Leading zeros don't count. Leading zeros don't count. This is 3 significant figures. Captive zeros count. This is 4 significant figures, and this is an infinite number of significant figures. The fewest number of significant figures I have is 3. So 0.516 times 0.172 divided by 0.0821 divided by 380.2. And I'm going to get, I'm going to write this down right here, 2.84 times 10 to the negative 3. This is moles of carbon tetrachloride, right down there like that. All right. Rounded to 3 significant figures. Now what we're going to do is we are going to now convert this into gram using the molar mass of carbon tetrachloride. So 1 mole of carbon tetrachloride. And now we need to calculate the molar mass of carbon tetrachloride. So 1 carbon, 12.011, plus 4 times 35.453. And both of these have 3 decimal places. So I'm going to have 3 decimal places for carbon tetrachloride, and that's 153.823 grams of CCl4. Right, I have 3 significant figures here. I have 6 significant figures here. I have an infinite number of significant figures because that's a definition. So I'm going to take in my calculator 2.84 times 10 to the negative 3 times 153.823 divided by 1. I'm going to round this number to 3 significant figures. That's 0.437 grams CCl4. And that is my final answer on this problem. Oh my goodness. You are watching The Crazy Head Chemist. And this is a crazy problem. Well, it's not really a crazy problem. And I'm not really crazy. Anyways, I hope this is looking good for you. We have one more problem to attack. And let's see if we can hammer that one out here right away. All right, so let's do that last problem of this worksheet. Here we go. Last problem of this worksheet. It says the following. A container has 0.5 moles of chlorine gas, 2 moles of hydrogen gas, and 1.5 moles of xenon gas at a total pressure of 780 with a decimal millimeters of mercury. What is the partial pressure due to each gas? Oh my gosh. This is actually a Dalton's law problem. And that is the total pressure is equal to the sum of all the individual pressures. So the first gas is chlorine. So partial pressure of chlorine, that's Cl2, plus the second gas is hydrogen. Partial pressure of hydrogen is H2, plus the third gas is xenon. So the partial pressure of xenon. So Dalton's law is the total pressure is equal to the sum of all the individual pressures. So what I do have is the total pressure of the system, and that's 780 millimeters of mercury. That's right here, 780 with a decimal millimeters of mercury, right there like that. What I don't have is the partial pressure of any of the gases, but I do have the mole values, and the mole values are the proportional to the pressures. So if you double the amount of gas, which is moles, then you'll double the pressure. So what we're going to do is we're going to take our 0.5 moles of chlorine for our pressure times X plus the 2 moles of hydrogen times X plus the 1.5 moles of xenon times X. Okay. And now what we're going to do is we're going to sum these numbers up here. So 0.5 plus 2, that's 2.5 plus 1.5. So 2.5 plus 1.5, that's 4. So that's 4x is equal to 780. That's with the decimal. And now what we're going to do is divide both sides by 4. Then I will get x is equal to 195. So that has 3 significant figures because that decimal right there on the 780, that 0 counts. Okay, so this is what x is equal to. Well, none of my pressures are equal to x. Okay, so what we're going to do is we're going to solve for the individual pressures of each gas. So from here, we're going to say partial pressure of chlorine gas. What does that equal? Well, that equals 0.5 times x. So that is going to be 0.5 times 195. So in my calculator, 0.5 times 195, that is going to equal 97.5 millimeters of mercury. And by the way, that does have 3 significant figures. This does not include the significant figures, okay? Then what we have is the partial pressure of the hydrogen, and that is equal to 2x. So that's going to be 2 times the 195, which is x. And that is going to be 390. 390, that's going to be a decimal right there, millimeters of mercury. So the partial pressure of hydrogen is 390 millimeters of mercury. We have one more to do. Let me zoom out so I can try to attempt to put all this here on one page. Partial pressure of xenon is equal to 1.5x. So that is 1.5 times the 195. And that's going to equal 293 millimeters of mercury. Just like that. That also has 2 significant figures. Okay. And these are the rounded numbers. And then so the partial pressure of chlorine is 97.5 millimeters of mercury. The partial pressure of hydrogen is 390 with a decimal millimeters of mercury. Partial pressure of xenon is 293 millimeters of mercury. Okay. If you wanted to check your work, you should be able to add up and sum up these 3 numbers, and they should be very closely approximating the 780, which they do. If you have the unrounded numbers, they will actually equal the 780 exactly. But these are rounded numbers, so they will be very, very close to the 780. All right. That is a perfect example of Dalton's law of partial pressures. I'm hoping that you subscribe to my YouTube channel. I'm hoping that you give me a thumbs up on this video. I hope you enjoyed it. And I hope you have a fantastic day. And don't forget, I'm the Crazy Hat Chemist. I'll see you next time for more crazy videos. Love y'all. Bye now.